So after evaporation, change in volume is, let us call it delta V. Okay, equal to V vapor into dA minus V liquid into dm equals to delta V equals to V vapor minus V liquid into D. So let's say it is our equation 3. So now if we combine this equation 3 which gives us value of delta V and this equation 2, okay, which gives us the value of delta Q. So we have so we can say that from equation 2 and 3 we have delta Q. From equation 2 we have delta Q equals to L dm, and from equation 3 we have delta V equals to V vapor minus V liquid into dm. Okay, so it gives us that dm amount of liquid absorbs an amount of heat delta Q and it converts to dm amount of vapor, and in this phase transition change in volume is delta V. Okay, so and during this process temperature remain constant. So we can write during this phase transition of phase transition from liquid to vapor, temperature is constant. Therefore, if we combine this and write it like this, del Q del V at constant T, as the temperature remain constant during this phase transition, then del Q del V equals to L dm by V vapor minus V liquid into dm. Okay, or del Q del V at constant T is equal to L by, so this dm and this dm will be cancelled and we will have L by V vapor minus V liquid. Okay, which is again, so this gives us the absorbed heat per unit volume, okay, during an isothermal expansion, okay, or isothermal process, because temperature is constant, which is basically the phase transition. In this case, during this phase transition temperature remains constant, so this is an isothermal process. Okay, and this gives us the delta V is the expansion in volume in this case due to absorption of delta Q amount of heat. Okay, now from equation 1, if you look at the equation 1, you will see that this delta Q delta V at constant temperature is equal to T del P del T at constant V. Okay, so from the equation 1 you will see that this is equal to T del P del T constant V. Okay, so here you see I have written it wrong, it will be del P del T. Okay, del P del T constant V. Okay, in the equation 1. Okay, so here you see from equation 1 we have del Q del V constant T equal to T into del P del T constant V. So here, so del Q del V constant T is equal to this term, which is L by V vapor minus V liquid, which is again equal to T del P del T constant V. So from equation 1. Okay, so now if the volume of the system is kept constant. Okay, now if we do something different, that now we keep the volume of the system constant and we increase the temperature. Okay, so if the volume of the system is kept constant and temperature is increased slightly, then what will happen? Then also the liquid will evaporate, but the equilibrium system will be disturbed and a new equilibrium state will be achieved. Okay, and the vapor pressure will also change, and then once the equilibrium state is achieved, a new vapor pressure will be there for the saturated vapor. Okay, so earlier what we did, we increased the volume but temperature, we kept the temperature constant. As a result, the liquid evaporated but the vapor pressure remained constant, because the vapor pressure is a function of temperature only. It does not depend on the amount of liquid or vapor or even the volume of the system. But now what we are doing, we are keeping the volume constant and we are increasing the temperature. Now as we are increasing the temperature, and we know vapor pressure is a function of temperature only, so the vapor pressure will change, the saturated vapor pressure will change, and also the equilibrium state will be disturbed. Okay, so as a result, what will happen? Now the liquid again will evaporated, and the liquid and the vapor will achieve a new equilibrium state with a new value of saturated vapor. So now the vapor pressure has changed from the previous value, because we have now changed the temperature, and to be precise, we have increased the temperature. Okay, so del P del T gives us the rate of change of pressure with the constant volume. Okay, so the rate of change of pressure with respect to temperature and constant volume at any volume, okay, is equals to rate of change of the saturated vapor with temperature at the saturated volume. Okay, so this pressure is for any pressure for any volume. Okay, and this P is for the saturated vapor pressure at the saturated volume. Okay, so now if we use this relation in equation 3, therefore from equation 3, okay, it was equation 4. Okay, suppose this is equation 4. Okay, so from equation 4 we have del P del T at constant V equal to, here you can write saturation. Okay, instead of V we will write saturation, because the rate is same for any volume and the saturated volume, equals to L by T into V vapor minus V liquid. Okay, so here you see we have, if you ignore this one, we have T del P del T constant V equals to L by V vapor minus V liquid. Now the process we said here, the temperature is changed. Okay, so the temperature is not constant, it is varying. So what we'll do, we will write the expression for del P del T at constant V and we will bring the temperature on this side. So therefore we have this del P del T for the saturated volume, the volume of the saturated vapor, equal to L by T into, so here we had this T and we have brought the T on the right hand side. So T into V vapor, specific volume of vapor, minus specific volume of liquid. Okay, so this is the, so here you can write it is the volume of saturated vapor okay, and this is the Clausius-Clapeyron equation. Okay, so this is the Clausius-Clapeyron equation. Okay. Now here you see in this equation, specific volume of vapor is always specific volume of liquid, right? Therefore, this quantity del P del T is always positive. A specific volume of vapor is always greater than specific volume of liquid. So this quantity, this term is always positive. L is positive latent heat, and this is the absolute temperature. It can never be negative, so it is always positive. And this is also positive always. So therefore this term is always positive. Therefore this term del P del T is always positive. So with increase in temperature, vapor pressure will always increase. It will never decrease. Okay, at constant volume. Now this Clausius-Clapeyron equation is derived for a particular phase transition, which is evaporation. But this Clausius-Clapeyron equation is valid for any phase transition. Okay, so it is valid for any phase transition, like between solid to liquid, liquid to vapor, or solid to vapor, vapor to solid, etc. So now we can state one generalized form of this equation, where if V1 and V2 are the specific volumes of a substance in phase 1 and phase 2. So this phase 1, suppose here phase 1 is the liquid, has a specific volume of V1, and phase 2, suppose here in our case the phase 2 was the vapor, which has a specific volume of V2. Then del P del T at constant V equals to L by T into V2 minus V1. So this relation of Clausius-Clapeyron equation is applicable for any phase transition, where V2 is the specific volume of phase 2 and V1 is the specific volume of phase 1.